How's everyone doing? How's the homework projects and homework assignment coming along? That machine should be fixed. I mean, I had to shut off the power, let it for a few minutes, then it won't come back on for some reason, then it came back on for some other reason. So it's working fine. So as people started the homework projects, the threading part, you don't have to be on the console to do that program, right? So you can do your program wherever, and as long as you can find a multiprocessor, test it either remotely or on the machine, right? And the homework assignments are due on Friday, the written part, right? So today I'm going to take you back with the atomicity and the transaction stuff we were talking about in the last class, right? So before we left, we were talking about adding transactions to the operating system and sort of giving a little hint on how it may be different from databases and how they deal with the stuff. It's the same concept, but the little differences, right? So are there any questions so far about this or some of those and stuff? So I'll continue back with where we left off, right? So we talked about having a log, keeping every write on the log, and like I think you pointed out, having a log forever would, you need to have a lot of storage, a lot of stable storage to store all the logs, and more importantly, you need to be able to go back to the log to replay everything. So if you have a failure, like the machine crashes or something, you have to go back in the log all the way to the front and then come back, because you have no idea what is actually being committed on the memory and what is being in the stable storage, right? So whatever is in the stable storage, you expect it to be accurate and correct, but anything else in the non-volatile storage could have been different, so you need to be able to replay it back. So the way you deal with that is through checkpoints. So basically at some point, you write a transaction record called checkpoint. And before you do that, you flush everything from non-volatile and volatile storage into the stable storage. So you flush first all the records that are in the volatile storage into the stable storage, all the modified. So basically you flush everything that is in your volatile storage into your stable storage, and then write a checkpoint record. And from that point on, the only transactions you need to worry is anything which started right before you wrote the checkpoint record, right? Every other record should have been committed in the main memory or in the volatile storage, and that would have been flushed to the stable storage when you did the checkpoint. Does that make sense? Right. So when you want to replay, you go back in the log to find the checkpoint record, and from that checkpoint record, keep going backwards to see the last transaction. That's the only transaction which it hasn't committed yet, because you don't have the commit record for that. Every other transaction would have committed, and any modification that they did to the volatile storage would have been sent to the stable storage when you did the commit. So you can only write a commit record after all these records have been written out, right? So this is one way to, so essentially you can clear out all the log records which happened before this transaction. So you can get back the storage from the log for these transactions. Can you see reason why you would not want to do checkpoints too often? Why checkpoints? Yeah.
If you flush all this stuff out of volatile storage, you're essentially pausing the system momentarily while you're writing that, and you take away the performance if you have like 1,000 users in there.
Yes. So the answer is, when you're doing the checkpoint, you're basically kind of stopping the system and flushing the stuff out, right? So if your system is up and running, it's making modifications. So when you're writing a checkpoint record, you're saying at this instant, everything which is in the volatile storage would get to be on the stable storage, right? And you have to essentially start the system for that to happen. You can't have the system changing underneath the checkpoint record, right? Because at the point that checkpoint is done, the system is in one stable state. So you're trading off the system performance. You can't have the system running while you're doing this stuff, right? So you don't want to do checkpoints often, but on the other hand, if you don't do checkpoints, then the log records can get fairly long, which is not as much of a problem on databases as it is on if you do it in an operating system, right? In a database, you don't really care about how big the log is because you're worried about, so you're operating on a different scale. You're operating on data and you're operating on databases and file storage and stuff like that. Whereas in operating system, you want things to be fast. So you don't want to stop the OS at some point, but you also want to manage the storage space. So you want to do different trade-offs. Right? So we are bringing all the stuff to be able to say something about threads. One of the things I mentioned last class is if you have multiple threads and they're executing and then they're doing their stuff, right? You can make the program very predictable by letting only one thread run, which is not what we want to do. So we want these threads to run as much as possible in parallel, but we want to be able to say something about what order they happen, what order they proceed, right? Because otherwise there's any number of ways where the threads can proceed. So if you imagine, if you have multiple threads all operating on stuff, right? You could, depending on how the thread gets assigned to processors, any one of them can make progress before the other ones. There's no ordering implicit in how these things work, right? And that may be a good thing because that's what you really want, but then also you want some kind of a notion to say, you want the flexibility, but you also want to be able to say something, right? So to bring that notion, we introduce the notion of serializability, right? So before we get there, first, so we have these concurrent operations, right? We define a notion of schedule, which is any execution sequence of how things happen, right? So if you have like 4 threads like this, a schedule may be, so if you call this thread 1, thread 2, thread 4, right? A schedule may be instruction from here, 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 or here, 2 instructions here, 3 instructions here, and so on, right? So schedule gives all the possibilities of how these transactions can interleave with each other for somebody who's looking from the outside. So if they're working concurrently, depending on how many processes you have, how the scheduling happens, you can have any way they kind of interleave, right? So does interleaving depend on the number of processes? What does interleaving depend on? Do you think it depends on the number of processors, or would a single processor make it more predictable than a multiprocessor? Let's take it. Yeah.
Well, in a single processor, they only have one place to go.
Mm-hmm.
Multi-processor, you have to pick what runs and where it runs.
Mm-hmm.
So there's more complexity to figure out.
Yes, and I think it's partially true, right? So in multiprocessor, it's highly likely that any one of them, so the interleaving can be on an instruction by instruction basis, right? On a single processor, it depends on how often you get preempted, right? So if each of your operation was to preempt this stuff, then essentially you behave like a multiprocessor. But if the preemption doesn't happen often, right, then you run for your time quota, then somebody else runs, then somebody else runs, right? So this is the notion of a schedule, and there is no right or wrong schedule. That's how these things run, right? So then we introduce the notion of a serial schedule. So serial schedule says that if you, in these sequences, if you define a transaction, right, define this as a transaction, right? So if you define these as transactions in your code, because you have a big transaction, end transaction kind of stuff, right? So if it's a serial schedule, it says that the transactions are in serial order, right? So one of the possibilities is you have T1, T2, T3, T4, right? So which says that transaction 1, and then transaction 2, then transaction 3, then transaction 4, right? It does not say that this has to be the order. So you could have T2, T1, T3, T4, right? What it says is you cannot have T1, T2, right? You cannot have something operating parallelly at the transaction level, right? So you're forcing these transactions to follow one another, right? So that you can figure out what the dependencies are. So if you're talking about transactions as, in the database parlance, as if you're trying to do checking account and stuff, right? So this may be you're depositing money into your checking account. This may be taking money out of the checking account. So one or the other happens as individual one, right? Depending on which way it happens, it may or may not be good for you, right? So if you deposit checks into your account in one transaction and withdraw the money in the other one, the reverse order may be not what you want, right? But we don't worry about that. We just worry about one thing happens and then the next thing happens. So any one of these these two are valid, and this is not what we want. Okay, so this is a valid schedule, but this is a valid serial schedule, right? And in fact, there's n factorial choices. So you can have any number of ways that these things can happen, and you still define them to be serial schedule. So if you force them to run like this all the time, right, then the system tends to be slow because you're making everything go one after the other. So we want something like this to happen, but we want the system to be able to behave like this, so we can say some things about how this system works, right? So we want to be able to schedule these operations internally, so what may actually happen is something like this, but from somebody who's looking outside, this is how the behavior will be, right? It looks like one transaction after the other transaction finishes, right? And that's what we're trying to do. So we're trying to get performance and predictability, right? So in order to get to that point, we define a notion of a conflict, right? So conflict is if you have two transactions operating on the same data, right? If one of them is a write, we define them as a conflict. And if both of them are a read, we don't say anything. We don't know anything, right? So let's take these two transactions, which is what we want to kind of interleave, right? So in this transaction, suppose you operate on variable x and you operate on a variable x here. If these two transactions read x, we say nothing. But if one of them writes, then that's a conflict, right? Because it depends. Then the order in which you see the output depends on that write finishing, right? Because the write has influence on this transaction. So if this write finishes first, right, then this transaction should either see the previous value or the next value. It can't see the half a transaction. So that's the notion of a conflict, right? And then we define a notion of how. So if you don't have conflict, right, those operations can be done simultaneously or switched around, right? Because if I'm reading the same value on two different transactions, if I'm not modifying anything, so it's equivalent whether T1 reads it first or T2 reads it first, right? As long as things are not returned, it's not a bad thing. Why we're doing this is we want to be able to figure out under what circumstances this would be equivalent to this or this, right? So we're adding this notion of a conflict. So let me move to the next slide to show how we want to do that. So on the left, right, there are two transactions, one in blue, one in gold, and they're operating on two variables, A and B, right? So a serial schedule would be all of one transaction and all of other transactions. So the first transaction does read of A, write of A, read of B, write of B, and the second one is the opposite, right? So now you have a transaction on to the right, which is sort of like this. These two are interleaved. So the read of A happens, and then read of A happens on the other transaction, and so on, right? So we want to see whether these two transactions are equivalent, or what we call conflict serializable, right? It is conflicting, but we want to be able to see if we can find the equivalent on like the first one, right? If you can say that, then essentially we are getting all the benefits of the first one, where we can say one transaction happens after the other, but still have them run on a multiprocessor in parallel, right? So is that clear why we're trying to get to this point, right? So this is the second one is good for performance. The first one is good for us to understand how a transaction should work, because we expect transactions to be atomic. We don't want transactions to have partial values, right? So what we do is, like I said, if there is two operations and one of them is a write and one of them is a read, there's a conflict. If there are two reads or read from a different value, then there's no conflict, right? So the way we work through this is we leave the first two writes alone, right? On the blue section, the read A and write A alone. Then we look at the next two interleave instructions, right? There's the write A in blue and read A in gold, and they conflict, which means that we can't swap them, right? If there's no conflict, then we can swap them. So, but if you look at here, right? If you look at the blue write B, and then the blue read B and the write A in gold, they don't conflict, right? Because they're operating on different variables. So they can happen at any one order. So what we can do essentially is so this is the stuff we have over there, right? These two do not conflict because they're operating on different variables, which means that if these two happen in any order, things will look the same, right? If you're trying to interleave these things, right? Because they're operating on different variables, so we can swap them, meaning we can move the B here and write A here, right? Because that interleaving could have happened and it would still behave the same. It still would not make the transaction do something that we didn't expect, right? And now we can do the same thing here, because these two are reads on different variables. So essentially we can move RB here, RA here, right? So now we can do the same thing here, because these are operating on different variables. So you become like B here, right A here, and then this and this are operating on different variables. So is that clear what I did? So I defined two operations on two different transactions to be in conflict if they operate on the same variable and they're doing a write. If they're operating on two different variables on two different things, then they're not in conflict. Then you can have them run at any one order, right? So what we're trying to do is, if you have one transaction, another transaction, if they run either separately or interleaved, if you can't tell the difference, then that's okay. That's what we want. We want the stuff to be faster, but not be able to tell the difference. The only way we cannot tell the difference is if they're operating on totally different stuff, or if there's no potential write which can affect a future read. I seem to have lost a whole bunch of people, right? So is the notion of why we're trying to do this clear? So let's look at these ones, right? Let's look at the notion of a transaction, right? So when you want to do a transaction, remember we said transactions should be atomic. We want these transactions to have all or nothing semantics, right? So if you wrote a program which looks like the one on the left, right? And it's trying to make some modification. Within the transaction, it calls the transaction begins. It does some operation. It does a read, write, what have you, right? and then there's another transaction which does read, write, what have you, right? What we demand is it's atomic, meaning the first transaction should happen all or nothing, right? So the first transaction does a read, write. So the second transaction, when it comes in, it should either be able to read the first instruction on the goal read, the read A, should either read the A which was written by the transaction or something before. Is that clear? So you have a variable called A, right? And you have a variable called B, right? And transaction 1 is the blue one, and transaction 2 is the gold one, right? On the serializable stuff, right, on the first goal read A, when it reads a value of A, it should either be the value of A which was written by the blue write, or which existed before, right? So it should either be the value which happened. So if this is the order in which events happen, right, I should either be using the value of A which came from the transaction before 1 at this point, or which happened after 1. I cannot use a value which is partially in the middle. Does that make sense? I'm not allowed to use a value partially, so I have to make sure that all the read A, read B, write B is noticed by the goal transaction as it is, or none at all. I cannot have something halfway through, right? So the one way to ensure that happens is if you go to a no preemption single-threaded model, which is what the serializable conflict would say, which basically says one transaction happens and the next transaction happens. So there can be no conflict. There's no way you can read a partial value in the middle, right? But that's incredibly slow because now you're making the program run, like in lockstep. So you want the first transaction to completely finish, then the second transaction, then the third transaction, and that's slow, right? Again, we are not restricting ourselves to say transaction 1 should happen, then 2, then 3. It's okay whichever order they happen. Either be T1, T2, T3, or T3, T2, T1, or whatever. But they cannot interleave. Right? They can happen in any one order, but not interleave. Right? So this will come into play if you have a struct with, right? If you have a set of code which is, let's say, swapping these two variables, and you have another transaction which swaps these two variables, right? If you interleave them, then the results are undefined, right? Because this transaction is doing something halfway through, the other transaction is doing halfway through. So we don't want the system to behave like this interleave, but we want to implement as much interleaving as possible in order to get better performance. And that's what we're trying to do, right? So if you look at this graph on the side, it doesn't look like it's any faster because if you assume that each line takes 1 time unit, it looks like it's taking 8 time units, right? But that's not really true because then that gives us a way to schedule these things differently. So if there's no conflict, they can both run in parallel, right? And that's what we're trying to do with this swap business, right? So if you are operating on one variable and something else is operating on another variable, right? I can do them at any one order because the other one does not depend on this one, right? So that's why you can run them both in parallel. So yes, in a transaction model, I don't want to see something partially till I finish what I have to do. But if I don't really care about that variable, I can run. I can let this thread run, right? And that's the logic we're using here. If two threads don't share the same value, two transactions don't share the same value, right? Then they won't notice the fact that these transactions are sort of violating the atomicity principle because they're just reading different variables. You only have a problem, you want to make sure that if they're operating on the same variable, you do something, right? And more clearly, if they're operating on the same variable and they're both writing, then that means you have to say something about which should say that what should see what, right? If you don't ensure that, then transaction 1 may have changed a value, the other transaction may see a partial value. Yes?
Okay, I understand like why the schedule and wait is allowed, but could you explain one more time like why that's better? Is it just because of performance or
Which one? The
conflict serializable schedule?
Oh, so the conflict serializable schedule is basically it's the set of instructions which happen on an actual machine, right? So so this is what we want to achieve, and the reason why the second one could be potentially faster, right? Is so if you run it like this on a single, so if you're running it on a single processor, this is sort of how you would look at it, right? So if you look at each one of them as a time stuff, you say time 1 I do read A, blue read A, time 2 I do blue read B, and so on, right? So obviously you can't be running too fast. If you're running on a multiple processor, and each one of them is running on a different thread, right? The first read A, right? So if this is the order we want to run, so if it's conflict serializable, it means that you can either run transaction blue, gold, or gold, blue. We can't have gold and blue interleaved, right? So let's assume that blue has to go first and then the gold has to go next. So the possible interleaving that we can have is we have to have read A, right? So those two reads can happen in parallel. Sorry. So you can take it back. The blue read A has to happen first. The blue write A has to happen next. And after blue write A happens, the gold read A can proceed immediately and not wait for the whole write stuff, right? So if this were to happen, essentially the completion time, so if they both came in at the same time, completion time for blue is 4 and the completion time in the serial schedule is 8, right? Whereas here it could be 6 and depending on what order they come, right? You can actually go faster. Did I manage to confuse you? Right? So depending on what order you come, right? So if you were to come in 2 clock cycles afterwards, potentially on this one you can finish faster, right? Because now you don't have to wait for the whole transaction to finish. So after the blue one finishes its write A, the gold one can proceed and do its read. It can't do anything with the B because the B depends on the values that are yet to be produced by the blue line, right? So it's not possible to move the gold read B and write B right after write A and read A and write A, right? But we can have this interleaving going on. Yes?
I understand that, but is the conflict serializable schedule hurt by context switching?
No,
It's not.
it shouldn't be.
Okay.
So context switching basically says that, so if these are, so you're not allowed to context switch from one and run the other, right? So conflict serializable says that this is the only order that we know is serializable conflict serializable, right? You are not allowed to context switch before you do the blue write A and do anything here, right? You're allowed to context switch from these two and go do something else and come back.
Okay.
But the order is still retained, right? So if you change the order of anything, then it's no longer conflict serializable. And I'm going to leave it as exercise to you, right? So if you change the order of how these things should happen, so for example, if you move the goal read A and write A, or move the goal read B and write B right after the goal read A and write A, right? That'll be a different schedule, right?
Okay.
We can try that. So basically, if you move it up, right, then they depend on stuff. You can't do the swap because they depend on those variables. And if you do the swap, you won't get to this schedule. You get to a different schedule, right? As long as you're not able to get to a serial schedule, it's not conflict serializable, right? So if you move these things together, then it is a schedule, but it's not conflict serializable. In which case, these two transactions won't have this property, right? And we're not saying that every transaction has to have this property, but that's the stuff you expect on a serial for transactions to work, right? So your system of, so if you expect serial schedule from a concept level, your system can only schedule these things in a conflict serializable fashion to get performance and still make it behave the way you wanted them to. That makes sense? Right? So as a programmer, if you're trying to write transactions, then you know it's guaranteed that transactions are atomic, which means that you expect it to have a serial schedule. The OS can do its tricks as long as the schedule is conflict serializable. If the schedule is conflict serializable, then an external viewer won't be able to tell the difference between whether it's serial schedule or it's a conflict serializable schedule. If you can't do these transformations that we said, if they're operating on same different variables, then you can swap the order in which things happen. If they're operating on the same variable, if they're doing reads, you can swap any which way you want. But if you're operating on the same variable and one of them is right, you cannot do anything, right? So you can't reduce from here. If you can't reduce from here to there using those transformations, then that means that this serial is no longer conflict serializable, which means that you can no longer guarantee atomicity. And so there's a potential for some transaction to see part value of the other one, right? So how many of you, I forget how many of you actually took the database class, right? So I'm guessing that you probably went through this a lot more gory details in that course, right? If you didn't, you should have, right? This is the one thing that you expect in a database, right? The database concept. So you can have a very slow database where every transaction happens one after the other, right? Like sort of what you have, but you don't want you want this ability to move this stuff, right? In the example I have, it's just read and write, so it's not obvious why you would want to swap these things, right? But in real world, these operations can be fairly complicated. So read A may be integer and B may be a 1 megabyte file, right? So read of A won't take the same time as read of B, right? So databases will go to a lot of math on how to use this to schedule these transactions and stuff like that. For us, we can kind of stop with this one, right? So if a OS was to implement transactions into its kernel, right, it would have to worry about this stuff because it has to find schedules which are conflict serializable when it tries to do these threads. So it has to not only understand transactions, right? So OS, if you have transactions within the kernel, every time you modify some data structure, you have to have primitives to start a transaction, end a transaction. But the OS, when it tries to schedule these threads, has to say, I have to maintain conflict serializability, which means that if a thread goal, whatever is running for goal frees up, you may not be able to schedule it even if it's ready to go because it's part of a transaction, the other half hasn't finished, right? And how you do that and all those things is way beyond the scope of this class. And that's one of the reasons why all the operating systems struggle to implement any of this stuff, right? From a using perspective, it's very nice. From an implementation perspective, it's a lot more complex. So if things are not yet clear on how these things work, right, I encourage you to read the chapter and get back to me because this is one of the chapters where all the stuff that you read, the exact wording in the book is fairly important. So understanding what it says is fairly important, right? Otherwise you won't. So otherwise the transformation I said may not make sense, right? So read the book, and if anything is not clear, we can get back to it on Friday. Does that make sense? So I'll talk about two locking mechanisms, how you can use these things. So we want to do all this stuff because we want performance and some kind of a predictability on how these things work. So one of the ways to use locks to get this serializability is to define a notion of shared or exclusive locks. Right? Shared is many transactions can read the same variable, right? It's sort of like the shared locks mechanism. And if you do exclusive transaction, then only one transaction can be reading that particular construct, right? So databases again would have probably spent like half the course on the two-phase protocol, two-phase commit or two-phase transaction protocol. Essentially what you do is, in order to ensure that things are serializable, right? So the problem here is, it was all easy for me to talk about this transaction by drawing some number of, drawing certain things and then moving things around and say this transaction is serializable. But when you're trying to write an operating system, you're trying to figure out, when I have a thread, should I schedule this thread and will it violate something, right? You don't have the hindsight of having all this stuff and then trying to figure out what we can move around. So in order to be able to schedule the processes on the fly online, right, we look at two protocols which would restrict what you can do, and what you get in return is you can say something about the protocol. So the first one is the two-phase protocol, which has the growing phase and the shrinking phase. So during the growing phase, you can get all the locks that you want, and during the shrinking phase, you have to give up all the locks that you have. You either keep the lock or you return the lock, right? So if you follow this protocol, I'm not going to go through the theory behind how you prove that. You can ensure that it's conflict serializable. So if you have two transactions and you're using locks, and you acquire locks during the growing phase, and you give up locks during the towards the shrinking phase, right? And you never switch it, then that particular transaction, if you schedule it, would be conflict serializable. So when you write your code, if you want to ensure conflict serializability, an operating system which does not give that to you by default, if you follow this model, then it will be, right? This is called two-phase locking, because basically you go through a phase of locking and then you go through a phase of unlocking. You don't lock and unlock, right?
Professor,
Mm-hmm.
what would prevent something from happening though? Like if you had T0 and T1 of like T0 acquiring a lock for A, but T1 being also in its growing phase and acquiring like a lock for B, they both need
So
both. And then
that's one of the things I said, it doesn't prevent you from getting deadlocked.
well, but then what if like B released, or what if T1 releases B and then T1 operates on B? You know what I'm saying? What if one process ends up completely modifying data within the time frame of another process? Wouldn't that be a problem?
So if you have, if there's a, you mean lock A, and then this is thread 1, right? This is thread 2,
Like, yeah, exactly like the last example. But,
and this is doing what? Lock A?
well, say T1 acquires like lock A,
Mm-hmm.
and then T2 requires lock B,
Okay.
and then finishes operating on lock B.
Okay. Okay.
This is like after T1's already, started, but T1 already has A, but it's waiting on B.
Okay. So that will come to the next one as deadlock,
Okay.
right? So yes, if L8, if it needs B, right? Actually, in this particular example, things will proceed, right? This transaction hasn't even started yet. It's kind of in the starting phase. So this will wait for this to finish, and then things will proceed, right? Which is sort of what we want, right? We're not defining that this should go first or this should go first. If this was what happened, then this will actually finish and this one will start later, right? If what happened here is, if you want to acquire lock A here, right? And they both did the first instruction, then they are trying to proceed to the next phase, then that causes locking. I mean deadlock, right? Because they are both waiting for the stuff, and we'll see in the next lecture what next slides what happens, right?
Okay.
So yeah, this does not prevent deadlock. It only makes the you can say that these are conflict serializable. Doesn't prevent deadlock, right? So the other way to implement this is using timestamps, right? I am definitely not going to go through the details on this one because it's, I don't know if you went through logical clocks and system clocks in databases, right? If you haven't, it's one of the most classical things that you would want to study in computer science. You know, Leslie Lamport had, I'm not sure how many have heard of Leslie Lamport, right? He's a great mathematician who actually did a lot of cool stuff. And one of the stuff he did was to have the notion of clocks, right? It's a 6-page paper, and it's written in 77 or something. It spawned a whole bunch of field of stuff after that. And it's one of those papers where every time you read it, something something new happens to you. And I'm not going to go through this class because it's big, more deeper than what we're trying to do, right? So they defined a way to figure out what you can say about the order, about the partial ordering or full ordering of how these instructions happen. The effects of that is felt not just in the operating system but also in architecture, where you're trying to do the same thing. You're trying to interleave different instructions, right? So have you guys taken a course in architecture? If not, you'll take a course in architecture. One of the things that you're trying to do, you're doing the exact same thing in architecture, trying to speed things up by moving things around, but not make it look like anything different to the user, right? So they define the notion of clocks and what causes events and stuff. So they define a new calculus based on that. All I'm going to say is like the artifacts of how that helps us, right? So one of the notion is, if you have transactions and if you give transactions a time, right? If you put a time on them, either the wall clock or notion of a logical clock, right? You'll use a wall clock if it's a single machine and it has the same clock, or if you're using two different machines, then the clock may not be synchronized. One clock may be moving ahead than the other one. Then you use a notion of a logical clock. Let's keep the notion of a system clock for now. So if all of us are operating on the same clock, right? Then basically we can all make progress on transaction. We can all do stuff differently, right? But before you start a transaction, I want you to write down the time you started a transaction, right? And we define that any transaction which happened before me will go, and any transaction which happened after me would have to be rolled back, right? So if there is something here, let's say there's a shared variable here that we all want to operate on, right? So the way we proceed is, before I start, I say, I'm going to start at time 11:22, and then somebody will say 11:23, whatever, right? And then we all get to modify it whichever way we wanted. So the person who said 11:23 may have come in here, made the modifications, but when I come back from an older time, then basically I should take precedence. So you undo all the changes that the person did, let my transaction go through, and it's undefined what you do with the other one, right? So basically that defines order. You define order based on time, and if things are out of time, happen at different orders of time, you roll them back, right? So you have a notion of a write timestamp and the read timestamp. And the write timestamp says that for a particular transaction, what is the timestamp of the transaction which operated on that last, right? So if you have two transactions, one at 11:22, one at 11:23, you keep a track of which one went through last. So if 11:23 went through first, you keep that in mind, right? So that's the write timestamp, and it's a similar thing for read timestamp. So essentially what you do is, if you get a new transaction, right, whose write timestamp is before what you have, then essentially you have to undo your stuff to let the other one happen, right? So there's two transactions, right? One is 11:22, one is 11:23. Right? This is when they started. So they proclaim themselves to be whatever. So which means that from now on, if these two transactions conflict, this will always win and this will have to be redone, right? Because this happened before this, right? So if during the execution, I see some instructions from here first, right? From this transaction first, it will update the last successful write from a transaction to be 11:23, right? The W timestamp. So, and then if some instruction from here comes in, then I will undo it, right? So this is another way of solving the problem. Basically saying, I define that whichever order you came in first into the system is the order that you're going to get. If anybody else, if there's interleaving, then I undo and roll back, and that way I ensure conflict serializability, right? And this way you kind of proclaim. So if you have like this, then in this system, this transaction will always go before this, and anything done by this transaction will go before this, right? And the way you do that is to undo the changes. You let the transaction go through, then you undo the changes, right? The difference between this and the prior ones is this one will never stop. It'll either let you proceed or it'll undo what you did, but it won't slow things down, right? So in the example that he pointed out with the locks and stuff, right? The second transaction, if this one started to run, this one cannot make progress, right? This one will have to wait because it's trying to wait for. I'm not talking about the deadlock case. I'm talking about the case where the transaction 1 wanted lock A and then lock B, and in the second transaction got the lock, right? So in this case, the first transaction would have to wait. Whereas in this model, you let everything proceed, but you do lots of undos and stuff, right? I'm kind of going through them fairly quickly, right? In the book, it's half a paragraph, right? So it has all the information that I just said, but you would have to do a careful read on what they're saying, right? So, but the idea here is I let any transaction go through, make any modification, but if a transaction from a prior time comes, then I undo everything that was done by the new transaction and let the old transaction go through. The way the reason why I can do that is all the transactions are logged, so the log has, the previous value and the prior value, and like I said in the earlier class, they're all idempotent, so you can go back and forth on a transaction model anytime. So I can undo any changes which are done. So if anything happens later, you move them back, right? The notion of time here is completely arbitrary, right? For some reason, you have to say which one should go first, and that's why you use a system clock, and that's the reason why you can use a logical clock or some number, right? All you need is a monotonically increasing number. Then you can say this transaction should go before this one, so you define an order, right? I seem to have lost many of you, but the problem, the thing is, what we talked about today is not a trivial thing, right? So, but I strongly encourage you to go back and read the book and try to work these things through your mind of what happened, right? What we learned today is very important, not just for this class, but in terms of what you see in actual systems and why systems behave certain way when they do, right? So we probably won't be talking too much about why does Vista have to wait, Microsoft Vista have to struggle so much to bring transactions, right? Like all the other constructs. But this is part of the reasons why these things are so complicated, right? You have to ensure some things. So these things define a notion of what we can guarantee and still get performance, right? So there's a lot of math and stuff behind it, but so I look forward to seeing, if you have any doubts on Friday, right? I'll see you guys on